Hi everyone, I'm ABHINAV KRISHNA and I'm currently pursuing data science and artificial intelligence in IIT Roorkee. Today we will be covering about LDA and some calculations in LDA, and I would be particularly answering two questions in LDA which we are going to talk about it later. So let me first introduce you to LDA. Basically, LDA is a technique which is used globally to reduce the dimensions of the data into a lower dimension so that we can do better analysis on them. It is used in many fields like machine learning and data retrieval, like bioinformatics or biometric. Now, let me tell you about some basic steps that we perform in LDA. The first step is to calculate the separability between different classes. That is, we call that between class variance. So like this is the data, uh, right? Suppose this is of class A and this is of class B. We first calculate the variance of the between classes, right? This which we call SB. And then the second step is to calculate the variance in the class itself, like the distance between the data points itself, which we call SP. Okay. And then we find a lower dimension or a lower space by maximizing the distance between the between classes and the minimizing the distance in within classes. Let me explain this to you visually. So suppose this is your data matrix and W1, W2, W3 are your classes and X1, X2, Xn, these are your data points, right? It's okay. So what you do first is you calculate the mean of these classes individually and you subtract them, which we say mean centering data, which is this D. And then we can calculate the within class matrix, that is SW, by this, by using um, like W1 minus U1 transpose into W1 minus U. This is how we calculate the variability in within classes, and we add the variability of each class and sum them to form SW. Similarly, we have got the mean of each class. We get the total mean, and that's how we calculate the SB matrix, right? Uh, like this is mu1, this is mu2, and we say mu1 minus mu transpose into mu1 minus mu as SB1. And similarly, we get this for all the classes and add them to get SB. And now we finally say that the direction which maximizes the between class variance and minimizes the within class variance is this. I'm going to talk about this, how this is derived. And then we select the largest eigenvalue and we project the current data into this eigenvector. What questions will I answer today? So basically, I'm talking about main agenda of my PPT, which is the role of matrix SV, SW inverse SB, and why we are considering the maximum eigenvalue of that. I will explain this thing later. And the reason behind the direct formula for getting the direction vector in case of two classes. Okay. Let me first explain the first question. Fine. To calculate the between class variance, the separation distance between different classes is denoted by mi minus m, will be calculated as follows. So what does mi minus m denotes? Mi is the mean of one class, okay, which is projected into a lower dimension, and m is the mean of all the projections of the mean of different classes. Okay, so M is the absolute mean of the classes, and Mi is the mean of the particular class, which has been projected into some lower dimension, right? So for calculating SB, we say distance, that is Mi minus M का square, is W transpose into mu I. What is this W transpose? So um, W transpose is the transformation of the mean of the classes or the current class into a lower dimension, and then we project those two means into a lower dimension, and we are taking the distance between them, right? So this equation becomes, yeah, so this becomes W transpose, as we get this equation, and we by following some matrix calculation, we get this W transpose into mu I minus mu into mu I minus mu transpose W. Okay, um, right. So this is your SB matrix, W transpose mu I minus mu into mu I minus mu transpose into W. Uh, okay, this I have talked about this earlier. Now, how do we calculate the within class variance? That is the variance between the data points of a particular class, right? So, which is actually consider like these are your data points of a particular of one class, and you are calculating actually the distance, the variance of all the data points within this class. And with because you are using variance, so you first calculate the mean of this class. So we get W transpose Xi minus W transpose mu j. Mu j is the mean of this class, the whole square, and SW is the sum of all the variance of these classes. So uh, we use sigma, right? And that's how we get SW. Now, why we are calculating this SW and SB? Let me talk about that. Okay, so the main aim and the main theory behind LDA is that we are actually taking some transformation into these data points into some like a lower dimension, such that when you project these data points into a lower dimension, the distance between the difference between the distance between the classes is maximum, and the distance between the within classes is minimum. Okay, so basically what you are doing is uh, uh, what you're doing is let's consider a matrix or a, a constant JW. So what you're doing is like you are maximizing the ratio between the between class variance and the within class variance. Okay, and basically we have to maximize this term. Okay, and we have to find that projection vector, that is the W. Okay, we have to find W such that it maximizes this function JW. Okay, so this problem becomes an optimization problem where you are doing W star such that it is R the max of JW, right? So basically we are finding this W star, which is the projection vector, okay, and with on which the data points is projected, which maximizes this JW. I think it's clear. So now you know why we have this optimization problem, that we have to maximize this term. So we definitely differentiate it, and by differentiating it and dividing it by some terms, this term, we get this. Okay, and this one is actually your J. which we took earlier. And this formulates into SBW equals to J into SW times W. Okay, so what is our aim? Our aim is that we have to find J, maximum value of J, right? So consider SW to be a full rank matrix. Okay, so we can take an inverse of that. And suppose it's not a full rank, then we can consider some pseudo inversions. Okay, so if we take this as invertible, this becomes SW inverse SB times W is J times W. So now we know that we have to maximize this J. And you can see that this has become actually an eigenvalue. J is actually an eigenvalue of this, right? So to maximize this J, this has to be a maximum eigenvalue of W, right? A maximum eigenvalue of the eigenvector W. So that's why uh, we actually say in this process, we actually find the J by maximizing this I think we know how to find the maximum eigenvalue. We solve this equation SW inverse SB and minus lambda I into W equals to 0. So by doing this equation, we find the lambda maximum value of lambda using this equation. And then we say that after getting the maximum eigenvalue lambda, we calculate the W matrix, right? So this is the basic process behind uh, behind this, and see, mm, this is our equation, and then we find W and we project the original data into W, right? So I explained my first answer, the answer of my first question, which was why we are why we use why we are using the uh, why we are considering the maximum eigenvalue of this SW inverse SB. I think you understood why we are using SW inverse SB. And now I will be talking about this alternate equation. So there is actually, when there are only two classes, this equation of W star actually we can write a shortcut formula for that, which is SW inverse mu1 minus mu2. So how is this derived, and why we are directly saying that it is SW inverse mu1 minus mu2? I want to explain further about that. So previously we derived that SW inverse SB W is J times W. We derived this. Now, what is this B? B is the between class matrix. Okay. Now consider two classes which has mean mu1 and mean mu2. Now for this, SB reduces to mu1 minus mu2 transpose into mu1. Okay, mu1 minus mu2 into mu1 minus mu2 transpose, right? This is our SB for a dimensional two cases problem, right? Two classes problem. Okay. Now, if I write this equation as W inverse mu1 minus mu2 mu1 minus mu2 transpose times W is J times W. Now, if you see this quantity, this is actually a scalar. Okay. And remember, keep that in mind. We are finding W. So this is actually scalar because we are reducing the dimension of 2D into 1D. So this becomes a scalar. And thus, this equation comes out as mu1 minus mu2 This is actually also a constant. We know J is a constant, so we can write this as K and W, right? Now, what exactly is W? W is actually a direction. So we can ignore this K quantity, and thus W becomes SW inverse mu1 minus. Okay, so that's why we were able to write this for in the case for two classes, right? And thus I think we conclude this PPT. Thanks for listening.